Now I want to introduce our guest speaker, Dr. Alex G. from the Carnegie Observatories, who will talk to us tonight on a project called the First Stars. So, Dr. G?
Great. Can everyone hear me?
Yes, I can hear you.
Great. And so I'm going to share my screen now. Why is this not working?
Because it's live. It's always the answer, right? When it's live is when it doesn't work when you try to do it.
Right. Okay, so when I'm looking this way, that's towards my slides, and when I'm looking this way, that's towards your faces. So, great. Thank you so much for having me today. It's really an honor to be here and seeing some of the really beautiful pictures that your group has been putting together. That's, you know, one of my favorite parts of all of this. So I am currently an astronomer at the Carnegie Observatories up in Pasadena. And I am what is called a stellar archaeologist, and I'll tell you a little bit about what that is today. And there's a lot of different questions I'm interested in trying to answer, but the one that I'll talk to you about today is what the first stars in the universe were like. And so today over the course, I'll tell you about sort of why we know that there have to be first stars, what we think those first stars are like, and how we, as astronomers, are actually going to try and test that. And I should have gotten this video playing earlier. This is, this is one of a simulation of what we think the early universe could have been like right after the formation of the first stars and galaxies. And I think it's just this really beautiful fly through of this. It's a completely theoretical calculation, but I think it really lends, at least to me, is one of the reasons that I sort of got captured by this whole topic was, to me, I just think it's really beautiful. Okay, so before we start with the first stars, I want to give a little bit of context about our current place inside of the universe, and also just give you, show you one of my favorite videos that's been put together by the American Museum of Natural History. And so everything that's being shown in this, can you see my cursor? Someone nod if, okay, maybe, good enough. So this is actually all mostly real data that is being shown in this particular video. So what we're going to do is we're going to start sort of, this is our planet Earth, as of course we all know and just got to see a little bit. And it's surrounded by all of these satellites. And what we're going to start doing is basically zoom out from the Earth to the entire observable universe. Right, so what we've done so far right now is we've zoomed out from the Earth, which is that region over there, to the orbit of the moon. Which of course is where Apollo was. And the distance between us and the moon is 1 light second. And the way that I think about this, being a millennial, I guess, is I think about it in terms of text messages, which is that if I want to, someday we're gonna have a moon base up there and I want to text my friend on the moon base, it'll take 1.3 seconds for my text message to reach them before they can text me back. And over here, this is the sun, right? The sun is 8 light minutes away from us. So if you want to text your friend who's living on the sun, you send them a text, you have to wait 8 minutes for your message to go over there. And then hopefully they're still alive and they can send you a text back. And then it'll take, 16 minutes back and forth, assuming that they're paying attention to their phone. Probably they wouldn't be if they're in front of the sun. So let's keep zooming out then to the rest of the solar system. We'll see the orbits of all of the other planets going all the way out until Pluto, which I guess is no longer a planet, although always in our hearts it's a planet, at least in mine. But this is the solar system, and the distance between the center of the solar system and the outskirts where Pluto is about 4 or 5 light hours. So of course, I'm sure as all of you know, this makes it very hard to communicate with satellites like New Horizons that fly by Pluto and that sort of thing. So this is, the solar system is pretty big, but we're going to zoom all the way out, right? Whole universe, right? So let's keep zooming out to the next thing, which is now to our Milky Way galaxy. And this is, each dot over here is now sort of representing a star inside of our Milky Way. And we think that there's about 100 or 200 billion stars inside of the Milky Way galaxy. 100 or 200 billion stars is a lot. So the way that I kind of conceptualize this number is that that's about how many neurons you have inside of your brain, or about how many white blood cells you have inside of your body, defending you from COVID or whatever. And the total size of this thing is about 100,000 light years across. And so this is the galaxy that we live in. This is, I think of it as my home. But we're gonna keep zooming out even further. So now each one of these dots over here represents actually a galaxy that we know of inside of the universe. You can see that there's like some clusters of galaxies and they form these sort of actually patterns, the same patterns that we were just seeing in that video with the baryon acoustic oscillations. So these patterns over here, which are sort of clusters of galaxies and characteristic distances corresponding to those sound waves, we see all of those things out there. And at the very furthest distances, we actually see quasars, which are basically lit up supermassive black holes. So those are some of the brightest objects that we can see, and we can see that those are sort of the furthest objects that we can see right now. But we're not done yet. We haven't reached the edge of the universe. That's just the farthest objects that we can see. If we just keep going back and keep going back, eventually we see it's like a giant plasma sphere that's surrounding us in all directions. It's kind of a horrifying thing to think about, but it's not a very cold plasma. But this plasma sphere that's around us in all directions, and that's actually basically the edge of everything that we could possibly see. Those are the initial. It's the afterglow of the Big Bang. It's called the cosmic background radiation. And this coloring over here sort of indicates it's called inhomogeneities inside of the temperature. So actually, if you were to sort of look in different directions on this sphere, like this direction over here and this direction over here, actually the temperature is almost identical. Right now it's about 2.7 Kelvin, and that is, and it's equal on all directions of the sky to about a part in 100,000. But each of these little ripples over here is sort of what sets the seeds for the growth of everything that comes afterwards. But at that time, very early on in the universe, everything's just like completely smooth and homogeneous to a part in 100,000. And so the way that I think about this anyway is that at that point in the universe is really boring. It's just like this smooth, homogeneous plasma. And there's nothing interesting like stars or galaxies or planets in the universe at that time. And so I did this thing where I sort of flipped between space and time, right? Because once you start looking really far away, you start looking back in time. And this, again, is sort of the furthest back that we can see. So this is a nice view, I think, if you're sort of a spatial thinker. For me, I'm actually, I guess, more of a temporal thinker. And the way that I think of this is you take this sphere, the furthest distances are sort of the earliest in time, and then the next closest distances are the next point in time, and then the next closest distances correspond to the next point in time. So you can sort of unwrap this sphere into a timeline. And so that's what we have over here, which is basically a brief history of our entire universe, where I've taken the sphere and put it at sort of the beginning of the universe. And where we are today, which is the center of the sphere, is over here on the right. And that's about a little less than 14 billion years after this time over here. And so the history of our universe, it starts with the Big Bang. We see this afterglow of the Big Bang over here. After that, there's a period called the Dark Ages, after which the first stars, the first supernovae, and the first heavy elements actually come into place in the universe. After that, you get the first galaxies. About 9 billion years after the Big Bang or so, our sun actually forms. And of course, over the course of the rest of this time, you get things like the Earth, life developing, and things happening all throughout the universe. So I think this is a really brilliant. We kind of actually know the history of our universe really well, which is a really surprising thing to me when I first learned that. So the time period that I really want to focus on today is just this first part over here. And this is the era of the first stars and galaxies. So again, on the left over here, this is about 400,000 years after the Big Bang. And over here is about a billion years after the Big Bang. So about a little less than 10% of the universe. And so after this period over here, where the universe is just completely smooth, there's like nothing going on at all. We have a period that astronomers, many people will refer to as the Dark Ages. And it's called the Dark Ages because it's almost literally dark. There is photons sort of out there in the universe, but there's no stars or galaxies or anything that are sort of lighting it up in the way that we think of the universe today. But that changes with the development of the first stars over here. And these first stars, I think anyway, are really interesting conceptually because it's this, we have a picture of what the universe looks like over here before any of those things form. And then what you can literally do is take those measurements, put them on a computer, put every single possible law of physics that you can think of onto the computer, and then push go. And what you can do is literally follow from the beginning of the universe, or at least this measurement that we have over here, all the way down to the formation of the very first generation of stars. And that's a unique thing that I think you can do over like the course of any time inside of cosmic history. So what I'm going to show you now is a video of what we think the formation of one of those first stars could have been like. So this is zoomed all the way in. We literally followed all of the material being pulled together by gravity, and then what ends up happening actually is it gets pulled into a disk. So we're right now getting like a top-down view of this disk, and I'll start this playing now. So the disk is sort of spiraling like this, and the material is actually accreting through the disk onto the star in the middle. And so this is sort of a proto first star. And what you can see is that this disk is very turbulent, and there's all sorts of things happening over here. So the disk is breaking up, forming potentially multiple first stars from this single collapsing cloud of gas. And from these simulations, when you look at them, these stars, like each of these little things over here, ends up being really, really massive, like typically 10 to 100 or even 1,000 times the mass of our sun. And one of the things we know about massive stars is they live really, really short lives, and they like to explode as supernova. So what we think all of these first stars do is at the end of their life, they do something like this. So this is like a very zoomed out view. So the first star that's forming is just indicated by that cross, and it's at the very center. And it's so bright that it's actually blowing a hole in all of the gaseous material that's around it. And so over the star is now sort of going to start nearing the end of its life, and it explodes as a supernova. And you saw that little white puff of material. I'm going to rewind it and play it again from over here. So at the end of its life, it sort of explodes a supernova, and it has that white puff. And that white puff is really important because that is the first time in the universe that we actually have heavy elements. So after the Big Bang and during all of this time, the universe is actually basically almost entirely composed just of hydrogen and helium. And the very first time that you get anything heavier than hydrogen and helium and a little bit of lithium is actually with the death of these very first generation of stars. So that little white puff over there is the first time that you get heavy elements in the universe. And so what do I mean by heavy elements? I mean things in the periodic table that are basically heavier than helium. So this includes things like carbon, which is making up the organic molecules that each of us is made out of. The nitrogen and oxygen that's in the air and the air that we breathe and the water that we drink. The sodium that all of us are probably not supposed to be eating too much of. The aluminum foil that is wrapping the the food that we're not supposed to be eating a lot of the time. The silicon that each of you is watching this particular presentation on. The phosphorus in our DNA, the calcium in our bones, the potassium that makes our brains run, titanium, the iron in our blood, nickel, and basically all of this stuff that makes up the world around us. The first time in the universe that stuff exists is that little white puff that happens with the death of the first stars. So I think this is, to me, like true origins. Like that's one of the things that really drew me to the first stars, to studying them, is that it really, it felt like you're reaching the very origins of where everything in the universe today comes to be. So a lot of what I've showed you so far, this picture of what the first stars are like, it's theoretical. So we take, we know how things start, but then we put things on a computer and look to see how they turn out. And then there's a question of like, how much of all of this stuff over here have we actually seen? And the answer is this, which is, we have this very narrow slice over here with the Big Bang afterglow. And we actually have, pushed out to about seeing stars and galaxies at about 1 billion years after the Big Bang, and we keep pushing this further and further. But this whole gap where the first stars actually form is just not explored by direct observations at all. So this sort of, is like, okay, so we have this beautiful picture. How do we actually see what's going on with it? And so so astronomers in general, unlike any of the other historical sciences, we get to cheat. So if you're a paleontologist or an archaeologist, you never actually get to go back in time. But astronomers who are interested in the history of the universe do, because as you look far away, you're looking back in time. And indeed, over many decades, we've been putting together larger and larger telescopes that are enabling us to basically see further and further away, further and further back into the beginning of the universe. And indeed, hopefully in about a year and a half, the James Webb Space Telescope will be up and running. I think it's going to launch. It's scheduled to launch in about a year, finally. Whoever made this graphic was very wise and just put future here instead of putting any particular date. But when this telescope goes up into space, it's going to be sort of what we think will allow us to peer the deepest that humanity has ever done into the history of our universe. And the question is this telescope going to be able to actually see the very first generation of stars? And it turns out, unfortunately, the answer is no. What people have calculated is that you actually need like a 100-meter telescope, so something like 330 feet in diameter, and you can't have it on Earth. You either have to build it in space or on the moon, and between those two things, on the moon is probably a little easier. And so this is like totally impractical for us in the near future. And so we're actually not expecting, at least I don't think in my lifetime, I will ever be able to take a picture of a first star with a telescope. So we have to do something else if we're interested in studying this first generation of stars. And the way we do this actually has to do with that puff of material that comes out, those very first heavy elements. So as I said, one of the key things to remember is that this very first generation of stars, we really think that they're all massive, and that means that they all live short lives and they all explode as supernova. And so when they explode as supernova, again, they put out that puff of heavy elements the first time they explode. When they explode, that is the first time that heavy elements are out there in the universe, right? And what happens with these heavy elements is they don't just go nowhere, right? They go out into the universe. So those newly synthesized heavy elements, they sort of, explode out in that puff, and then eventually gravity will pull some of that material back into a star-forming nebula. And what we think is that once you hit this second generation of stars over here, you can form both small stars and big stars. So both low mass stars and massive stars. And the interesting thing about this now is that these low mass stars can actually live a really long time. The things that are less than about 8/10 of the mass of our sun can actually live longer than the age of our universe. And so these stars will actually survive from the beginning of the universe until today. These stars over here will not, right? These stars over here are massive. They're going to explode and die. And what they'll do, so short time for me is 10 million years. So they'll live for a short time, and then they'll explode as a supernova. And when when these stars explode as supernova, they'll also create newly synthesized heavy elements, right? And so now we have two generations of stars explode, spewing out heavy elements into the universe. And those combined amount of things have now enriched this next generation of stars. And you can imagine this continuing on throughout the history of our universe, right? You have the first generation of stars that explodes and creates some heavy elements. And this next generation of stars explodes, creates a little more heavy elements. This next generation of stars explodes, creates a little more heavy elements, and so on and so forth, all the way until today. And what we know is that in a galaxy like our own, you start with 0% heavy elements, but by the time you've reached today, you're something like 5% heavy elements inside of our Milky Way galaxy. And our sun is somewhere over here at about 2%, made up of 2% heavy elements. And I think this is really cool because this buildup of heavy elements over time, over the lives and deaths of stars, it also traces like the entire history of our universe, right? Because this first generation of stars forms very early in our universe, and then this next generation of stars has more heavy elements that make it up, and then this next generation of stars has more heavy elements that make it up. And so the universe's composition evolves with time, and each star preserves the history of all of its ancestors that were born and died before. So you can kind of think of the composition of a star as a little bit like its cosmic DNA. So again, all of this traces the entire history of our universe, right? The buildup of heavy elements over time traces this entire process. So heavy elements you can think of as a sort of a clock. And so, but because we're made up of all generations of stars that were born and died before us, what that means is that the first stars, we think they're all gone today. But because they all exploded and died, some of their ashes continue to live on in everything, including like us, including you and me. And I calculated that about 1 teaspoon of each of us is made up of material that was synthesized in the first stars. So what's a teaspoon? So it's about half a pinky finger is about 1 teaspoon. So about that much of you is made up of material that was actually synthesized at the beginning of the universe by this very first generation of stars. Of course, it's not, it would be neat if you could concentrate it all over here in your pinky finger and be like, oh, all of those elements came from that very first generation of stars. But that's not how it works, right? It gets all mixed together with all of the other generations of stars. And so I can't pinpoint for you which carbon atom in your body came from the first stars. And similarly, when we look at a star like our sun, we actually, it's very difficult for us to actually tell which of those elements actually came from the first generation of stars. And so what I do as a stellar archaeologist, I basically try and look for stars that are right here. Stars that are born very early in the age of the universe that have been enriched, whose only progenitor is the very first generation of stars, right? So if we're looking at stars over here, they're sort of the sum total of every single generation of stars that has ever formed. But this star over here, its entire history is just the first generation of stars. And because these stars over here are low mass and they survive the entire history of the universe, they formed in the universe at that very early time, but you still can find them today. And this is actually why we call it stellar archaeology, similar to how archaeologists look for human artifacts to try and study the history of humanity, or paleontologists try and look at fossils of various sorts to study the history of the Earth. Stellar archaeologists look at very old stars that are still surviving today and study them in great detail to try and learn about what's going on in this very early part of the universe. And the way that you can find these stars is you can look at their content, right? So this very first generation of stars has no heavy elements inside of it. And this second generation of stars has almost no heavy elements inside of it. And so far, we found about 8 stars, which everyone agrees are these second generation stars. There's a lot more that people argue about, but there's 8 where basically everyone that I know anyway agrees that these are second generation stars. So let me show you one of them. So this image over here is an image of a patch of the sky where one of these points over here is a second generation star. So by looking at this image, does anyone think that they can tell which one of the stars it is? I see Frank shaking his head. Yeah. So I wouldn't be able to tell you either. Yeah, Steve's shaking his head too. Yeah, lots of head shakes, and I agree. Like, I would have no idea which of these things it is, and it's so it turns out to be that one, the one in the middle, and it's not even that bright one or that bright one over there. It's actually that little dinky one over here. So zooming in, it's that star over there. So that's a second generation star, but I guess how do we know that, right? It's maybe a little bluer than all of the other ones around it. And so that's not how we tell, right? The way that we tell is we actually take a spectrum, and it was fun to hear. I think I forgot who it was at the beginning of this meeting saying that they had just gotten into spectroscopy, which is exactly what I do, right? So we go to stars, and what you do is you effectively you hold up a prism to the star, and when that happens, it splits the light from the star into all of its different colors. And if you've ever done this with, say, our sun, so literally if you have a prism, or like a nice piece of glass, right? You can go outside during the day, maybe not now, it's not super, not right now, but during the day, on a clear day with the sun, hold up your prism and watch the light actually just get split into a rainbow of colors, right? And if you're very astute, you will notice that there are actually dark bands inside of that rainbow. So there will be several of these dark bands over here. And what those dark bands are is actually a fingerprint of what the star is made out of. So every single dark band over here actually corresponds to light of a specific color that is being taken away by material in the outer layer of a star. And so you can do this with the sun, but you can also do this with basically any other star that's out there. You take its light, you split it up into all of the different colors, and you look at the dark bands. And basically, the deeper, the darker the band, the more of that element. It's more complicated than that, but that's roughly how it works. Okay, so that's actually basically what I do, except that instead of going out and sort of looking at stars in the middle of the night, I do this with my favorite telescopes in the world. which this one over here is one of the two Magellan telescopes in Chile. It's called the Clay telescope. And we don't hold up prisms to them. That would be kind of cool, actually. But we use really fancy prisms called spectrographs. So this is a picture of me with my colleague Johanna Teskey, who was actually training me how to use this thing. So this is this gigantic thing over here, which is roughly me-sized, is a spectrograph that basically does the work of this prism over here to split the light basically into very, very fine colors. So just to give you an idea of like the type of thing that I look at every day. So if you take the light from your prism and you sort of rotate it on its side, and then you go from sort of the purple end to the red end, or the blue end to the red end, and basically sort of go along and look at the intensity of the light as you go along. That's called a spectrum, and that's what we are looking at over here on the left. So we've taken in this case, actually, it's just like a tiny patch of the purple over here, and we spread it out into all of these regions over here. And so these the darker the band over here, basically those small, the lower this will be. So if it was just sort of all smooth, you would be flat over here. But the different elements that are inside of the surface of the star are actually causing all of these absorption lines to happen. And this is really, really, for those who know, this is really, really, really high resolution over here. From here to here is angstroms. So that's about, oh gosh, what does that mean? It's 10 to the minus 10 meters. I'm not sure that means anything to anyone, but it's it's a 0.1 of a nanometer is one angstrom. So like, for instance, this line, this absorption that's happening over here is from an iron line, from iron that's absorbing in the surface of the sun. This over here is actually from nickel that's absorbing in the surface of the sun. And you can see that all of these sort of little dips and wiggles over here correspond to different elements in the surface of our sun. So our sun is like 2% heavy elements. And what that corresponds to is that out of for every 31,000 hydrogen atoms, you've got about one iron atom inside of it. And what we look for is stars that look more like this. So it's basically flat, and you have very few of these dips over here. And that corresponds to much less of all of the other elements. So all of these other things over here that would be absorbing inside of our sun, they're just gone. And there's very small absorption features, these very small dark bands corresponding to iron. So this particular star has one iron atom for every 310 million hydrogen atoms inside of that star. And this one's even more extreme. You can see that like there's no iron at all, maybe a tiny little thing over here, and each of these things is absorbing a lot less. So that means that there's one iron atom for every 6.8 billion hydrogen atoms inside of this sun. It's like 100,000 times less or something compared to the sun over here. So these stars have so few heavy elements inside of them that we think that they are second generation stars. So this star that I showed you earlier, so these two stars actually, they still had some iron lines. This star that I showed you earlier, we looked throughout its entire spectrum, and this is just one of the lines over here. And literally in the entire spectrum, we could not find a single absorption line, not a single dark band that corresponded to iron. And so we only have a limit on how much iron there is, right? So we say, if it was this strong, there would have been one iron atom for every 20, I can't even count the zeros, 20 billion, 20 billion hydrogen atoms inside of this star. So this is one of two stars that we know of where we have not detected iron inside of the star whatsoever. And it has this name. This is actually roughly the right ascension in the declination if you want to try and find it yourself. It's 17th magnitude, so it might be pretty hard. Okay, so when we find these stars, so first of all, we have to find them, and that takes a lot of effort. But once we found them, what do we do? Well, these stars don't have, they have no iron, but a lot of them do have a lot of other elements. And so this is actually a plot from one of my scientific papers. So the x-axis over here, each square over here, basically indicates an element inside of that particular star. This star over here, it indicates an element that we've measured. So we actually were able to measure elements like carbon. We were able to measure sodium, aluminum, magnesium. Sorry, I did that backwards. Sodium and aluminum, and then that's magnesium and silicon inside of this particular star. We also were able to measure some calcium, but we were unable to detect any amount of titanium, manganese, iron, or nickel inside of this star. And what that actually means, so when you look at all this entire pattern of elements, you can use that to actually learn something about what type of star exploded to produce this particular pattern of elements. And what we learned by talking to our theorist friends is that to produce a pattern of measurements like this, the ancestor of this star had to have been about 50 times the mass of our sun, which is pretty big, not the biggest it could have been, but definitely up there. And so this is one of the types of things that we can do with when we find these second generation stars. And the way that you can kind of think of this is basically this particular star has a lot of these relatively lighter elements, and almost none or very small amounts of these very heavy elements. And the picture that we think this is telling us is that at least some of the very first generation of stars exploded as something called a faint supernova. So supernovas, you may know, are the deaths of massive stars. When they die, they basically explode, they implode, and then they explode. And this is a particular type of supernova that's called a faint supernova. And the way this works is that, stars are like ogres, right? They have layers. At the end of their lives, they have a iron in the middle, that's the heaviest element. And as you go out, you have progressively lighter elements. And the picture that we think is happening over here is basically that when the star explodes, what ends up happening is basically it sort of mixes up all of the material that's in the very core of the star. And then what happens is, because we think that if the star is sort of really massive and very compact, it's not actually able to eject every single piece of material that was over here, whereas sort of the bigger ones probably can eject most of it. And what ends up happening is all of the material in the middle actually just collapses down into a black hole that ends up being in the middle. And so this is how you can get a star that has a lot of the lighter elements, but a small amount of the heavy elements, right? You basically, we're able to get out these outer layers of the star without the inner layers of the star. So you mix it up, you take a part in the middle, and then these parts over here, there's a lot of carbon. Almost all the carbon gets blown out of the star, but almost none of the iron gets blown out of the star. And so that's how you get a lot of carbon and almost no iron. So it's one of the things that's very frustrating about this field is that we only have about 8 second generation stars that everyone agrees are second generation stars. And one of the problems is that there's a lot more candidate stars out there that we know of that could potentially be these second generation stars. They're just too far away to be studied. Basically, they're very faint. The star that I showed you actually is sort of at the limit of what we can do right now. It's a 17th magnitude star. And it took about 30 hours on our 6.5 meter telescope to get the data that we saw. And so there's a couple of different strategies that we can do to try and find more of these second generation stars. And I just wanted to tell you about those because they're kind of neat things that are happening right now. The first strategy is that you can just try and find more candidate stars, right? So right now we've sort of done deep surveys in certain parts of the sky to try and find these second generation stars. But maybe you can actually do them across the whole sky, and that would actually let you find a lot more of these candidate second generation stars that are bright enough that we can study them in detail right now. And one of the things that's becoming really, really big right now is something called spectroscopic surveys. So when I right now go to the telescope, I basically take a single star and spread its light out to measure the properties of that star. But what these surveys have been doing for a while now is trying to measure the spectrum of lots and lots of stars at once. And so this is like a pretty cool way that they do this. This is a picture from the Sloan Digital Sky Survey. And the idea is that like literally you take a fiber optic cable and you put it where you would normally put your optics to look at the star. But because stars are positioned in particular places on the sky, right, what they do is they take a metal plate and then they drill holes located where each one of the stars that you want to look at actually is. And then someone during the day just goes and plugs a fiber optic cable into each one of these holes. And so you can kind of see over here, these are actually positions of the stars on the sky. And in this way, you can take like 1,000 spectra at once, as opposed to me right now, who's taking like one at a time. And this is how we're going to sort of mow through the sky and take a spectrum of everything that we can possibly find. So one of the programs that I'm part of is called the Sloan Digital Sky Survey. And in this next generation of it, there's been 4 previous generations, and the next generation is actually using a telescope both in Chile as well as at Apache Point in New Mexico to basically do this mowing of, like, literally they're going to try and do the entire sky. Every single part, every single thing they're going to try and get a spectrum of. So that's great. That will let us find a lot more brighter things to study. But at the end of the day, there's only so many second generation stars that are out there. And so at the end of the day, what we'll have to do is actually go to bigger telescopes in order to study these more distant possible second generation stars. And one of the things I'm really excited about is people are hoping to build telescopes of just ginormous size. So this over here is sort of a cartoon of what's called the 30-meter telescope. They are thinking they might build it in Mauna Kea. We will see about how that turns out. And it's called the 30-meter telescope because its mirror is 30 meters large. This is like a multiple story building over here. And this one over, so that will go in Hawaii, which can access most of the northern hemisphere. And this one over here is called the Giant Magellan Telescope, which will be built in Chile and also be able to access sort of the southern hemisphere. This one will be about 24.5 meters in diameter. So this is sort of what is on the horizon for people like me who do stellar archaeology, but that's not the only way to study the first stars. And I didn't want to go into each one of these things in detail, but we think that there's these very first generation of stars are massive, and they can span all of these possible masses over here, or at least we have to check to see if they're there. And so stellar archaeology is really good at looking at sort of biggish stars up to 50-ish to 100-ish solar masses. Stellar archaeology potentially, if our theories are wrong, there could be surviving first generation stars. That's actually sort of my hope, is that I'll find one of these. But we think these don't exist, but if we find one, that would completely change our theories of how the first stars formed. But there's also other things that you can do. You can actually look at merging black holes. You can look at something called a pair instability supernova. And you can also look, we can't see the first stars directly, but we think that they might seed the very first supermassive black holes, those quasars that are some of the farthest things that we can see. So there's this whole, as we get to questions, feel free to ask me about any of these things if any of those piqued your interest. Yeah, so that's what I wanted to tell you today about the first stars. I think I think it's a really fascinating topic. I hope you agree. And yeah, I'm happy to take questions. And I just wanted to play this last video put together by led by John Wise, but also actually Mike Norman is a professor at San Diego. So this is just a really beautiful thing. Yeah, happy to take questions.
Hi, Dr. G. I have some questions if you want to take them while the video is playing. What do you do for calibration sources?
Yeah, that's a really good question. So it depends a lot on what we are trying to do, but for the particular type of observations I showed, the very high resolution spectroscopy, we take 3 types of calibrations mostly. The first thing we take is a wavelength calibration. This is, you take an arc lamp, in our case it's thorium and argon, because those have lots of lines. And that tells us when we take our, I wish I had an image in here of the actual what the actual data looks like. But what it looks like is basically you have little chunks of rainbows that are all the way through, except the rainbows are in terms of the position. So you need a wavelength calibration to see what point on your image that you take corresponds to which wavelength or which color. The second thing that we take is something called a flat, and that's basically, that is used for 2 things. The first is it tells us on the, we use it to define where you actually need to look to get the data from your star. It defines the data, that complicated instrument sort of produces things in a very distorted shape. So you have to use the flat to help remove that. And then the there's actually two types of flats that we take. The first one is sort of for tracing it out, and the other one is for we turn on basically a lamp. It's called a quartz lamp. It's just a lamp, and it just and we put a diffuser in the front. So actually, we put a diffuser in front of the lamp so that it actually uniformly illuminates, or at least as close to as possible, uniformly illuminates our detector. And so the picture of me at the telescope, which I guess is this one, that's me putting the diffuser into the telescope, or into the instrument, sorry. Yeah, so that allows us to take sort of remove the spatial variations and at least find or mask the regions that are to sort of take care of the pixel to pixel sensitivities. And then the last thing that we usually take is a radial velocity standard. So we want to see how fast the stars are going, and we have a list of stars that we know have very stable velocities, and we take one of those just to make sure that our wavelength calibrations are okay.
Okay. Questions for Dr. G? There's one in the chat. I don't know if you can see that, Dr. G.
I can now. So the question is from Philip Blanco. Even stars in the lowest metallicity environments, dwarf galaxies, seem to need dust to form to provide seeds for accretion and to radiate away energy in the collapse. Do we have any theoretical understanding how stars can form dust-free, and what range of masses are allowed in the first generation of stars? Yeah, so that's a really excellent question. And it gets back to this, I guess. So there's actually, so the fact that these stars form in a dust-free environment, as far as we can tell, is actually why they are so massive. So that's sort of a thing that I glossed over. But yeah, as you say over here, the dust is really important for basically taking energy from this gas and just spewing it away, right? Basically what happens is these dust grains over here, there's all of the gas swirling around, and every once in a while, one of the gas particles transfers some of its energy to the dust grain, which heats it up. And then when the dust grain is heated up, it sort of radiates away that energy, and that allows this gas to basically remove its energy and gravitationally collapse. And when you have things like dust grains or even just floating pieces of carbon and oxygen, the gas is pretty good at removing that energy. But in this very first generation of stars, that's just not the case, right? There's none of that material there. There's no dust in the universe at that time, because there's nothing that the dust is made out of. And what that means is that it's really hard to remove that energy. And so what we end up having to do, and what the theory shows us in these calculations, is that you actually can only remove the energy through molecular hydrogen. And so what you actually do, so molecular hydrogen is basically two hydrogen atoms that attach to each other. So it's H2, H sub 2. And this is a symmetric atom, so it's actually not very good at removing energy. But what it does is it sort of, you can sort of do the same thing where you sort of hit it with a thing, you sort of spin it up a bit, and then when it stops spinning, it removes some energy. It's really bad at doing this compared to dust and compared to just any heavy elements in general. And what that means is that, like, essentially you can think of it as like the gas just stays hot all of the time and it can't gravitationally collapse. And so when you watch this over here, if you were to put a bunch of dust in over here, what would happen is this entire disk over here would be breaking up all over the place into lots of small pieces. In fact, you wouldn't even get a disk this big in the first place, because in the process of the material coming down, the dust would sort of trigger pieces of that collapsing cloud to turn into stars. But what happens here with these stars is, with this first generation, is that because there's none of that, it just sort of goes, and then you end up with this super big disk. That's why you end up with, and there's so much material over there, that's why you end up with these like tens of solar masses of stars that are so massive. So that's a really good question. And then the last part of this is, do we know what range of masses are allowed? And the answer is kind of. This is really the key question, because as we saw over here, there's actually lots of different ways in principle that we could study this, all of these different mass ranges of stars. So what the theoretical calculations seem to show us, the best state of the art ones that we have right now, suggests that almost all of the first generation stars should sort of be in this range. So about 10 to about 100 solar masses. We don't know that for sure. And what happens is basically every time people put in a new piece of physics or they get better and are able to run the calculations for longer, they get a slightly different answer. So sometimes they do get some of these very massive stars, and sometimes you sort of by chance manage to make some of these very low mass stars. But it seems like I would say, given our current best understanding, this is sort of the range. But the fact that I'm sort of very hesitant to, so I've told you a set of numbers. I'm very hesitant about that because we really just don't know. And that's why we have to look for signatures of these stars.
Good. Well, thank you. That was a nice question and answer. The next question for Dr. G. No. Well, so I have.
Oh,
I have
yeah, I've got a
question.
question.
Oh, go ahead.
Yeah.
just
Is there
for
a
everybody-
catalog of first generation stars that we can get to? Something that'll give us the magnitude? And are any of these stars bright enough that amateurs can see and measure the spectra?
Yeah, so they're actually, so those 8 stars, I could list them for you. There isn't like a formal catalog that someone has. There's not a catalog that someone is sort of actively paying attention to and keeping track of. The brightest one that I know of, oh gosh, so this star, I think this is the brightest one out of those 8. This star over here is 11th magnitude in visual. And that is, I think, one that you could see. The problem is at declination minus 38, so it'll be a little hard to do from here. But so that's what the minus 38 is over here. And this one's at declination close to minus 52. This was and so I'll say that actually it turns out that most of the searches that have been done so far have been done in the Southern Hemisphere. And that's just kind of historical because in the initial sort of the first spectrum that everyone took, they used an objective prism. So it's a giant prism with a very large field of view. And that survey was just done in the Southern Hemisphere. So that's where most of the people have looked. That's actually one of the reasons that we have to look throughout the whole Northern Hemisphere. So I'm hoping that we'll have a better, when this thing comes on line and starts sort of scanning the whole sky, I'm hoping that we'll have some brighter things that we'll be able to find. But I think the brightest one I know of, sorry.
Is there a way to follow that and perhaps get a list of those stars eventually? Or
the best person to ask will be me. Yeah.
Do you have a paper title that we can search on the internet and find one of your papers?
Yeah, so I think at the time there were 7, and this one over here, maybe the easiest thing for me to do is just send you a link to the paper rather than, I can't remember the title.
Okay.
The title of the paper is the name of the star.
Oh, a snazzy science title.
Yeah, it's not a useful title, but I can send a link if people are interested. And that one has a list of the names of the other stars. And then I'll also send a catalog of these 8 stars and where they're located.
so a good experiment would be to look at first generation stars and then second generation stars and compare them.
Yeah,
Maybe a science project for somebody.
Yeah, so that definitely is a good idea. And what starts getting really difficult about this is, and this is actually where I spend, like, that's a really good question. That's actually why I have a job. Like one of the reasons that I spend all of this time is trying to disentangle the generations of stars. So I think, so I'll say that we have sort of maybe like 1,000 stars that have low heavy element content, but not so low that we're certain that they're second generation stars, right? And what we don't know is how many generations make up those stars prior to that. And what we don't know, and so when you look at the composition of these stars, we don't know how to interpret it because we don't know how many generations of stars we have to add together in order to explain what we actually see inside of them, right? because I painted this picture over here of like this generation of stars forms, and just this one explodes, and then this one explodes, but it's not like that, right? Like what's actually happening is there's some stars that are forming over here and they're exploding, and then there's some stars that are forming over here and they're exploding. And this gas cloud over here, or maybe this gas cloud over here, is actually a combination of all of those things that are mixed together. And so at some point it starts getting really, really complicated. And that complication actually happens. Some people argue it happens over here. I have argued that before. And other people say it happens, more here or here. And that's just a thing that makes it really hard to go beyond the very sort of oldest stars, or the very beyond this generation that's relatively simple to interpret.
I've got a question. Some have suggested that there could be something you would call a dark star, which would involve dark matter. And how would that fit into your timeline, you might say? And obviously it would depend on what the interactions of dark matter actually are.
Yeah, that's a really good question. So there's sort of a couple of different, so I'll start with the fact that this thing happens at all is thanks to dark matter. So these things, there's not enough gravity to form these things fast enough if there's no dark matter. So all of these things are sitting at the center of the smallest star-forming dark matter halos that are out there. I think with dark stars, so I've actually heard it in two different ways. One of them is like completely made of dark matter stars, but I think what you're thinking of is what people have proposed is that dark matter might be able to collect inside of a star and be able to interact and basically add some extra energy to the star that would, on top of sort of the typical thing like nuclear fusion inside of that star. So the way that could manifest here, and it probably would manifest here, is basically it would heat up these stars. So when these stars form over here, it actually will affect what's going on over here. So it'll heat up the centers of these stars a little more than they would otherwise. And that will slightly change sort of the lifetimes of these stars and potentially, hopefully, potentially what elements they make, although I think that's going to be too hard to know. But the way that this happened, that's what the if dark stars mean a lot of different things, but in the one that I'm familiar with, that's what that would do.
Thank you.
Next question for Dr. G. Okay, well, I got another question till I find. Dr. G, when you do your collections, do you typically go to Chile or do you do it remotely?
Yeah, so I would say that until COVID, we always went. And there were two reasons for this. At least two reasons. The first is that we really like going. Going to Chile is, here, let me, oh, I'm sharing the wrong screen, but it's one of the most beautiful places to observe, I would say. It's just really, really clear, really, really stable. So this typical, like, we complain when the seeing is worse than 0.6, 0.7 arcseconds at our particular site. So that's one of the reasons that we go there. And then the other reason, of course, is that it's much better to be there to take the data and sort of make split-second decisions about what to do as you are taking it off. What we have done since COVID, so our telescopes shut down for COVID because Chile had a gigantic burst of COVID cases, but they've been slowly opening, and so they've actually just a couple days ago opened up the second telescope. So a couple months ago they opened up one of the two, and then December 15th they opened the second one, and so now they've set up remote observing. I guess the third reason is that the internet there is less stable than one would like. It has happened that people cut the fiber optic cable while doing construction in the area. And so it's become reliable enough that you can do completely remote observing now. There's a lag, it's precious seconds. When I go observing, I plan exactly what I'm doing, or at least I make a plan down to the minute. about what I'm going to do. Like I literally do things to minute precision because we don't get that much time on these telescopes. So you know, it's something like a typical group might get 2 nights a semester on one of these. So like 3 or 4 nights a year. At the Carnegie Observatories, we're fortunate that we can get a lot more, so up to 5 or 10 nights a year. But that's still not that many nights, and so you're going to plan out every single minute of those nights. And if there's an internet lag that cost you an hour, that can be pretty catastrophic, right? But I think, you know, it does cost a lot, and it's pretty bad for the environment for us to keep flying down. And so I think increasingly people will move to remote observing, especially now that we've seen that it can work pretty well.
Excellent.
I would.
Another question for Dr. G?
Dr. G, what did your parents think about your field, and how did you get start in astronomy? Were you very young, or was this just part of your life?
Yeah, so I'll say that I never thought I would end up in astronomy. And so I started interested in physics in general. So I was interested in questions about dark matter and dark energy. And when I was in college, what I wanted to do was go to the Large Hadron Collider in Europe at CERN and work there. And once I started working on that, I realized that those are collaborations of like thousands of people. You work on one tiny little part of a gigantic experiment, and you spend 10 years coming up with one result. And I just felt like that was not, you know, some people are okay with that, but me personally, from what I was interested in doing, didn't really appeal to me after I learned what that entailed. So I looked around for something else that I thought was interesting, and basically what ended up, I went to grad school basically not wanting to do physics and not necessarily astronomy, but what really captivated me was basically this picture of the first stars. I was like, I don't even know what it was. It was just, I just really like this topic, and I saw it and I was like, oh, I just want to know what these things are, right? Like, and it just seemed like a place where there was a lot unknown, and I would say there's still a lot unknown, and that's how I got into it. So the first time I will say that the first time I looked through a telescope, it was a 6.5 meter telescope, and since then I've been sort of trying to catch up.
Oh my.
Yeah, and so I will say that yeah, so that's the path that I took to being here. It was very much I was looking for things that I wanted to answer, science questions that I wanted to answer, and I ended up here. In terms of what my parents think, that's a very interesting question. They are very supportive. Neither of them particularly, I think. They're very supportive, and I would say that they're very excited that I am doing something that I really love to do. But I think if you asked either of them, what would you have wished your son to do in the future when I was like, I don't know, like 20 something, I don't think they would have chosen this. Yeah, but they're very happy.
Cool. Sounds like you were drawn in by basic curiosity.
Yeah.
Just something caught your attention. How cool. Another question for Dr. G? Okay, well, I have a question. Are the stars that you study, are they basically M dwarf stars?
Yeah, that's a good question. So no.
Oh.
And the reason actually so in principle, M dwarf stars would be the best ones to study because they are the most numerous by number. The problem is that there's 2 problems. The first is that they're pretty faint, so you actually can't see that far. And because these second generation stars are so rare, so I guess to give you, we've found 8 of them right in the whole sky, and we've combed through like hundreds of thousands of stars to find these 8. And so they're so rare that we're actually going out pretty far. So I think the closest one that I know of is a few hundred parsecs away. And most of the M dwarfs that are really well studied are sort of within a few hundred parsecs. And so we end up looking primarily in two places. We actually mostly look at giant stars. So the giant stars, because they're the furthest, and also because they end up, so giant stars are more luminous, right? And so the ones that are sort of closer to the end of their lives, they're just, we can see them further, and they actually have stronger spectral lines in general.
Is a particular spectral class?
We mostly look at K and M giants.
Okay.
Yeah.
All right. Another question for Dr. G? No? Well, I have another question. Have you thought about using maybe the Gaia system? Because they have low resolution spectra on there, at least to get candidates for you then to go back and verify?
Yeah, absolutely. So Gaia is going to be great. So they have low resolution spectra. I would say it's about a third the resolution, so it's not actually terrible. The main thing is that they haven't actually released any of their spectra yet. And so we're really, so the Gaia official third data release is scheduled to happen in like late 2021 to 2022. And that's when they will actually release those spectra out for us to look at. That will be pretty good because that will get us everything in the sky that is bright enough for them to take a spectrum. We'll still have to go and continue to follow them up with other instruments because in actually two generations of it, basically because the Gaia only looks around sort of a strong but still relatively weak infrared triplet line. And so you have to end up going to optical lines to see the actual content of these stars, but it will whittle things down a lot, that's for sure.
Okay. All right, another chance to ask Dr. G a question. We're getting to the end here. Don't be shy. Well, I think that's it, Dr. G, I guess. I want to thank you very much for a very interesting, unusual talk, very unusual area. I don't think we've had anything like this in our astronomy club, and I would just ask our members to give Dr. G a round of applause and thanks. Couple thumbs up.
Great. Thank you so much.
Thank you.
This was a lot of fun.
Okay, with that, I call the end to our December San Diego Astronomy Association meeting. Thank you all for coming.